Hi everyone. I want to continue talking about AC electronics and the math behind it. One of the problems with this alternating current is the sine and cosine nature of these things can become quite tedious pretty quickly. And dealing with all these phase shifts would involve a lot of trig identities and all sorts of complications. And we have a mathematical trick at our disposal that I want to talk about now. It's called a phasor. And this is the diagram that you might recognize when we talked about harmonic motion and its connection to uniform circular motion. Basically the idea here is you've got a ball that's maybe spinning around in a circle on a string, and it moves with uniform speed as it goes on the circle. It just spins around. And if we imagine the projection of that position on this line, this is going to oscillate back and forth. Okay? And in fact, the connection is just the cosine function, right? So there's a little right triangle here, and this is related. These lengths are related to the cosine, and so this oscillates back and forth in time, using the cosine function. And so what we're going to do now is basically use this relationship in reverse. So we've got an oscillation, and we're going to imagine a two-dimensional abstract space associated with this vibration. Now there's nothing physical, there's nothing really two-dimensional about an alternating current. But we do this in order to leverage the fact that we know how to deal with two dimensions using vectors. And so basically we're going to transform a trigonometric problem into a vector problem. And that's what these pictures over here represent. We've got a resistor, capacitor, inductor. These three graphs represent the same information that was in the previous video, because in the previous video I had sine curves here. And a sine curve is completely determined by its size, its amplitude, and its phase shift. Also the frequency, and that's also in the picture here. So those three elements define the sine curve. Well, the three elements are here. We've got a magnitude, which is associated with the peak amplitude. We've got an angle, which is associated with the phase shift, where we are along that curve. And then you've got to imagine these arrows are not sitting here like a snapshot, but they spin like this, right? They spin in time. They're moving around. And that's representing the frequency. So we've got all three elements captured. We've got the amplitude, the phase shift, and the frequency, all captured in this diagram. Now, the frequency is not critical. You don't have to. In fact, it's simpler if I had written these lines right along the horizontal in this case. Basically, I wanted to emphasize the fact that these are spinning. But this is the picture for a resistor. A resistor, the current and the voltages are in phase with one another. When one peaks, the other peaks. When one's at its max, has got its maximum along the x, the other's got its maximum along the x. They go together. This is Ohm's law. For capacitor and inductor, there is a phase shift. There is an orientation difference. And so, in this case, the current's leading the voltage, right? They're spinning this direction, so the current is in front of the voltage. Eli the Iceman, I is in front of the E for a capacitor. And for an inductor, the voltage is in front of the current. And so these are the pictures that carry the exact same information content as the previous ones, but now instead of dealing with sines and cosines, we're dealing with vectors. And ultimately, when we combine our electric circuits, what we want to capture is the net impedance. And that's what this Z symbol represents. This impedance is the ratio of the voltage to the current. Right? These all move with the same frequency, so they all have the same kind of orientation differences as we move through time. And the total net impact of everything is captured in this idea of impedance. Both resistance and reactance is captured in impedance. So the way it will work is that suppose we have a simple RCL circuit, a series circuit where we've got a resistor, capacitor, and inductor. the current flows through all three components because they're in series. So whatever current flows through one flows through the other. Which means that we should take these three pictures and twist them so that the current is all lined up, is all pointed in the same direction, because the currents are equal for our three components. And in fact, it would be even simpler if we took this and twisted it so the resistor were completely horizontal. So that's what we do. We take the resistor picture, move it so its current's horizontal. What that means is that the current for the capacitor must also be horizontal. I need to take this like this, right? So I've got current going this direction, voltage down. Got to take this, twist it around, current going this way, voltage going this way. So the currents are all aligned because we have a series circuit. The voltages are not. And so in order to calculate the net impedance of all the circuit together, I need to combine those voltages. And the way I do that is with my vector math. I've got a voltage, I've got a horizontal component representing the resistance. And I've got vertical components. You know, this one's going to be pointing down, this one's going to be pointing up, so they oppose one another. And so what I need to do in order to capture the net is to calculate the component horizontal, the component vertical, add them via Pythagorean's theorem. And that's where this formula comes from. You can see I've got the resistive component here, and I've got the reactive component here, and the capacitor and the inductor oppose one another because of this nature. And so this is just an example, you know, for different combinations of elements. We'll have a different formula. This is the formula for an RCL circuit in series.